The first unit of study for the course is going to be on prehistory, everything before recorded writing. We're going to start with the earliest hominids and kind of work our way how the course notes kind of work, as well as working towards getting in humans onto the scene. You're going to need everything in yellow, so this should go down into your notes. So we want to ask a very simple question of how do we learn about early humans, with the major problem being that there is no written language. Language dates back, or writing dates back to right around the invention of writing to 3000 BC, so roughly 4,000 years ago. So what we as historians, scientists, archaeologists, people who are interested in this have to do is be able to decipher what the life was like for these earliest humans or human-like creatures in reality from their garbage and what they left behind, and be able to piece all this together. So various different historians and scientists work together to try to piece this puzzle of human origins from, again, very sporadic pieces. So one group are archaeologists. And archaeologists learn about early people by excavating and studying traces of early settlements. If you've seen any Indiana Jones movies, it's a great example of an archaeologist. I'm going to pause 1 second. We want to be able to make sure we understand how the notes are going to work. If you see archaeologist is underlined there on the PowerPoint slide. If you pull out your study guides, you can see the first term there is archaeologist. And then we just very simply go and you can, for at least this one, fill right on there. The quiz is going to ask about archaeologists. You should know that they learn about early people by excavating and studying traces of early settlements. So kind of how the notes go and work here. If it's in yellow and highlighted, it's good to know. If it's underlined, it's one of the terms on the study guide. Those terms on the study guide, as you can see, will go in order with the notes. And if it's on the study guide, it's going to be on our quiz or assessment in one way, shape, or form. Archaeologists learn about these early peoples at an archaeological dig or an excavation site where they're going into the ground for the most part, removing layers of sediment and dirt to be able to properly place where and then thus when artifacts and bones were found. So as we just said, what are they looking for at these digs? One are bones, and bones can tell us a lot of information about a person or a animal, because we can pull some stuff there. We can tell what they look like. If you usually ask the question if anybody's interested in becoming a forensic scientist working with police at murder scenes and other stuff, and you can go and you can take a look at a skull or other bones, particularly from a human body, and that skeleton is going to move by muscles, and those muscles have to attach to bones. So you can look at attachment points on the bones, and from there you can see that obviously someone who can lift a lot of weights is going to have a bigger muscle that's going to put more stress on a bone to be able to move it, and bones are there to kind of give your body some rigidity and to be able to provide that counterweight to be able to lift something up. You can see that it's from there. So particularly say looking at how attachment points on a face work on the skull and where the muscles attach there, you can get a rough kind of clay outline with the muscles and then put skin over the top to give a rough estimation of what somebody would have looked like. Obviously, bones can tell you the height of a person. A tall person is going to have tall bones. A smaller person is going to have smaller bones. So we can get that from there. Bones can tell you a person's diet. A person who's consuming a lot of calcium is going to have different bones from someone who is not consuming that calcium. A healthy person, a person who's getting a lot of nutrients, is going to have different bones and how they're constructed and how they're preserved versus someone who is having a poorer diet. Disease can tell you diseases. Now, obviously, if you have something like bone cancer, that's going to show up in the bones itself. But we can go and we can do chemical analysis of bones and see that, oh, this disease causes this nutrient deficiency, which should show up in the bones. And if the bones don't have that, therefore, we can kind of work our way through there. They can also show lifespan. You can go and take a look at, I've got two kids under two in my house right now, my two daughters. They actually, my youngest daughter, who's 8 months old, has more bones in her body than I do. She's got, like, I was thinking, I don't know, you can check your biology class, like 256 bones to my 206. more bones. So you can go and take a look at that. Again, you can kind of go see how bones are shifting and moving based on someone's lifespan, as well as kind of going and seeing, almost like counting the rings on a tree to be able to see how long they lived. Artifacts are the other big thing that archaeologists are looking for. An artifact is any human-made object, so a tool, jewelry, and et cetera, et cetera, et cetera. And that's what we're doing. If it's human-made, or again, depending on your terminology, made by the hominid, there, that would be an artifact, particularly if you're talking about archaeology from a human, just human perspective. You get any object that has obviously been human made. And this is where, and we'll show you some examples, the trained archaeological eye is going to be able to spot out something that this is an artifact versus this is a rock, or this is a stone, this is a stone tool. And that's where the expertise comes in. And obviously, artifacts can tell us a lot of stuff. They can tell how people dressed, how they worked, how they worshiped, uh, what they did for fun, how they expressed themselves, all from the detritus and the debris and the garbage they left behind. And so, again, when we're looking at these ideas of no written language, think about all the stuff that you, when you're listening to this today, have consumed, have made, have left behind. And we usually ask the question, who's had breakfast this morning? We keep hands, and who's made garbage from that breakfast? And you can piece together parts of people's lives just from that bits and pieces of information. I like to say that the archaeologists are working in tandem with anthropologists. So the archaeologists are digging in the ground. They're taking the bones and artifacts, and some people might be wearing multiple hats, but in the theory in the book makes it trying to make a differentiation, then turns that stuff over to anthropologists. The anthropologists take the very scientific and measurements from the archaeologists and examine the artifacts at the digs. What anthropologists do is study culture. A culture is a people unique way of life. My culture, it might be slightly different from your culture, even though we look the same, we sound the same, we come from the same place, and that's what makes your unique thing. We like to say that if I invite you over to my house for dinner, I might serve you some foods that you have, and I might serve you some different foods. The same, vice versa. You might be over to dinner, I might be getting something different, and so that's kind of something to be able to go and think about and kind of through, and that's what makes someone's life unique. And that's what anthropologists and archaeologists are trying to do by digging into the ground to recreate these glimpses of early people's behavior. A third group of scientists are paleontologists. Paleontologists study fossils. So an archaeologist might be going back in just 50 years, 60 years, or again, thousands of years. Paleontologists, the life has to be preserved within rock. And so we're very much going farther back in history, but still studying this idea of human origins. And a paleontologist doesn't just deal with dinosaurs. You can deal with other plants and animals or organisms that have died and then have their remains preserved within rocks. And they're going to use techniques to help date the fossil remains in the rock. And so that's what they're able to do. And these three groups all work together to be able to piece these puzzle pieces of what is life like for these early hominids, humans, other organisms on the earth without any written language. Archaeologists and paleontologists dig in the ground, anthropologists that examine what the findings are to be able to work together to put this puzzle pieces. So we usually like to play a couple of I guess games or discussions in class where we're going and taking a look at these various and assorted different items. We pull out the laser pointer. We can go and say, hey, what are these over here on the left? And usually we get the answer, oh, those are rocks, Mr. Cranmer. But these all have been shaped by human hands. And again, we're not talking about, let's say, 1 centimeter down here. We're not talking about something big and huge and gigantic, but we can see that these arrowheads have all kind of been shaped and moved. And this is the type of stuff that we're looking at. So it doesn't have to be as kind of obvious as maybe something, this bit of amber that's been shaped to look like an animal. We usually ask what animal. You got the ears, you got the eyes, you got the snout and the nose, a bear, a pig, what have you. It's less important about what it is than that this has been shaped by human hands. That we can go and we can see instruments like this and ask the question, what is this on the bottom right? And usually we play a good game of 20 questions before we finally reveal that this is for tattooing, right? That's ink, not a torch on there to be able to go and tattoo someone. And so that's the type of stuff that we go and we see. So an archaeologist are digging in the ground, these are some of the scenes that they go and they pull up. There's no letters, there's no YouTube channels, there's no Snapchat reels to be able to go through and examine what's going on. This is the information that we have. And looking through there, we can be able to go and ask certain questions and be able to see, hey, deliberate choices have been made. Simply the deliberate choice of burying these two people, not just letting their carcasses open to nature and anything else on there. They've been buried underground. They've been buried together. So there might be some significance there. We see some necklaces on both, so there's some significance there. Again, we have antlers at the top, and those are all things that you got to ask questions and begin to do. Do we have the answers for them? Maybe not necessarily, but you start to go and put this in a timeline, comparing with other sites. We start to think things together. Other notable things, we see a lot of seashells next to this burial. Now, that might not mean a whole lot if we go beyond this ridge here and there's the Mediterranean Sea or the ocean. But if these were, say, high up in the mountains where there's not a sea around there, then these become significant. And those are the type of questions, those are the types of observations that these archaeologists, paleontologists, and then the anthropologists are trying to make to put this picture together. Because not everything is delivered to us as, say, this Siberian wolf puppy from 12,000 years ago, with the pollen from its last breath in its lung, with its last meal still in its stomach, where you can get a fairly good estimation of what it is. And with the thawing of the permafrost in the Arctic, we're pulling out more and more of these animals like that. You've got our wolf puppy back down here, woolly rhino, woolly mammoth, and then you've got a young baby horse there that have been stuck and preserved for these years. They come back to us, but not everything is handed to us in a silver platter like this. As we're working our way through the two PowerPoints that make up this first unit, we want to just take a step back and make sure we understand that early human origins is very much an ongoing study with new discoveries happening all the time. I like to follow on Twitter. It's a bot that's just called Neanderthal News, where it just goes and spits at me articles of new findings just on Neanderthals and early humans. And again, that feed is constantly giving stuff, and they're all that do that. So make sure we understand we're going to present information to you, and by the time this video is recorded, it's early November of 2024. You might be listening it next week, next month, next year, 5 years down the line, and this might be out of date just because of how quickly things can change and how very little evidence we still have. Again, we're trying to create this puzzle out of, say, a corner piece here, a middle piece here, and then like a bottom left piece. And so it becomes hard to do when we only have these small bits and pieces and there's not a whole lot of links that we can make, although we're getting better and better all the time. So just remember that out of the billions of humans and human-like beings that have ever lived on the earth, we really only have confidently remains about 5,000 prehistoric individuals. So all these remains could fit in the back of a pickup truck because you've got this person's arm bone and another person's pinky and another person's pinky toe, and you're trying to be able to go and piece all this together, particularly how certain groups of remains end up in certain areas at certain times and certain layers with very skimpy evidence. So we're going to say a lot of things, and it's all backed up by very good science, but just note that this is very much still ongoing. We're making discoveries all the time, and something that I have read in my elementary school, I might necessarily not be taught in elementary schools today, 5 years from now, later on. It's going on all the time, and that's what very much this is trying to represent. That there's all these people, humans, Homo sapiens, and human-like ancestors that have ever lived, and we're still just finding the smallest fragments. So we might be going and getting someone who is maybe not a typical quote-unquote example of an organism at a certain time period, but that's all that we have. And so it's kind of going and saying, I've got all these videos on YouTube right now. If you're just judging me on one singular one, maybe that's not the best way over the course and breadth of the work. And that's the point we're trying to make. It seems like we maybe have a certain individual or a certain group of human hominids, but we might not have one specific individual, and we're trying to go and piece things out from there. So that's what this graphic is trying to get at, is that this skeleton, and it's not even a complete skeleton of one of the early hominids, is pieced together from 15 different individuals. So imagine a class of 29 kids, and we're trying to go and take a single bone from every single one and now trying to say this is what humans are like in Mr. Cranmer's class in 2024. It's not going to be a complete picture, but it's still better than nothing. And that's what we're trying to go and do here. So the whole point is this is trying to be able to piece together where we fit in the world, where we fit in the history of the world, where we fit in the history of biology on the earth. And that's what we're trying to get at and trying to discover as we work our way back to the single cell organisms and try to be able to piece together a family tree of what's come before, where we are, and what relation we have to not only the rest of the earth, but the organisms that are on there. And that's what we're going to kind of be working through in the next couple of slides and in the next PowerPoint or so in this early on, is to work from our earliest humans uh, ancestors towards what makes us us today. Because when we take a look at how DNA works and how we relate to other organisms on the earth, we can have a chimpanzee and we can have my daughter on there on the right, and the DNA of both of these animals is 99% the same. Okay, we share 60 some percent of our DNA with a banana. You're talking about a 99 point, I think 99.4% of their DNA is shared with the chimpanzee, 99.7 with the bonobo, and yet chimpanzees cannot communicate, cannot speak the same language that I have. The biggest sentence that we've been able to, if quote unquote, teach great apes to talk is, I want orange, give me orange, I want orange now. And yet I'm able to talk for 16 minutes now by this point and to be able to communicate. So that's the big difference here. Even though the DNA, what is that difference between the DNA here that allows for chimpanzees to walk and talk and act like they do and humans to be able to move all over the earth and land SUV-sized vehicles on Mars? And that's kind of where we're trying to go to be able to put the difference between these two organisms that share 99% of the DNA, and yet a human is fundamentally different from the gorilla on the right. And again, when we're talking about DNA, there's a lot of stuff where you can take this left and forth. But again, remember, you're talking about billions of different changes. So you take that 0.1% or that 0.3%, you times that by a billion, that gives a lot of different changes. So just take everything we say with a grain of salt. What we have, what we've been able to discover, and what we historians, educators, scientists, is pretty good at the moment, but it's all that we have that's representative. So it might not be quote unquote the best picture and the most quote unquote true, but it all we got. So what we want to understand is we want to work through this idea of hominids. And a hominid is any human or other creature that walked upright, specifically referring to species on their way to becoming human. So if we're starting with us right now in the class, in the year that we're taking this, Mr. Cranmer speaking here in 2024, and we work our way back as far as we possibly can, anything that walked upright and is on the way to becoming human gets this term hominid. And the earliest hominids are Australopithecines. And the big characteristic that they have that very much make a hominid, and everything else not, is that they walked upright and they had opposable thumbs. Not walking upright like, oh, I've got a treat over my dog, I can get him to stand up, or my cat's acting weird and it's walking on two legs for a little bit. It's that we are designed down to our biology and to our skeletons to walk on 2 feet, right, for long distances upright there. And there's changes in our biology to be able to accommodate that walking upright, as well as having opposable thumbs. An opposable thumb is, if you look at your thumb, the ball and socket joint that attaches your thumb to your hand. The ability for you to be able to take your thumb and touch all of your fingers in each thing makes it opposable, and is something that other great apes and primates lack, but we have. And that becomes, maybe not so great apes, but monkeys in particular. Australopithecines are about 7 million years ago, and these are the species that are the first kind of divergence from chimpanzees. So a lot of heavy loaded terms and big ideas when we're talking about evolution. We can be kind of get bogged down in details and bogged down in debate here. But what we understand is that two chimpanzees 7 million years ago had a baby. That baby looked like a chimpanzee, walked like a chimpanzee, talked like a chimpanzee, right, roller skated like a chimpanzee. It's just that that baby, right, with the small individual mutations or changes in its DNA code then gave birth to other babies, and that then started the line to where we end up today versus the line of chimpanzees that are also on the earth. So that's the big divergence that we have, and all humans, right, come and trace their lineage back down to that particular birth. And the Australopithecines are going to be the dominant species of hominid on the earth for nearly 5 million years. So we'd like to talk about and put this in the geologic space and perspective, just how long timeline is on the earth here. If we take a look at the history of the earth and we put that, say, in perspective of a football field, humans are really only allowed on that 1 yard line going 99 yards down the field on that 1 yard line on the last blade of grass before you get into the kind of that end zone line. And so that's how short humans on a geologic scale have been on the earth, particularly modern humans. So we start going back here. These guys are going to be along for these Australopithecines are going to be around for a very long time. Now, the archaeological evidence comes from a couple of different things. Now, your book is going to do it a little bit more group it by subjective. I've moved it in more a chronological order. The earliest known, and again, I'm talking about this is what we're pulling out here in 2024. The earliest known hominid archaeological evidence are the Laetoli footprints. And these happened 3.6 million years ago. This was discovered in 1978 by Mary Leakey of the famous Leakey archaeological team in Laetoli, Tanzania, which is like Central Eastern Africa. These are two individuals who left preserved footprints in volcanic ash. 3.6 million years ago, volcano erupts, spews ash into the air, falls down like snow. These two individuals walk through it, leave 80 feet of footprints in the ash. The ash then hardens farther into stone that's covered by dirt. It's preserved, and then it's discovered here. We know it's two individuals, and we'll show you pictures of it because it's two distinct footprints. We have a larger set of footprints, and we have a smaller set of footprints. And again, we say, well, what can we learn from that? Well, again, that's all we have are those footprints. So we can learn a lot, and you can find some videos online and be able to look at the footprints and be able to kind of analyze the walking style and the gait of these individuals. But we know that one could be a male, one could be a female. Right? Males tend to be bigger than females. We could have a older individual and a younger individual. You could have a mom and a dad, older brother, bigger brother. We don't know the relationship between the two. We just know that they're walking along for over 80 feet, and we have that. We're confirmed that. Now, the individual remains that we have that are the oldest are of the Australopithecine with the nickname of Lucy. So Lucy dates from 3.5 million years ago. She was discovered a little bit earlier in 1974 by Donald Johnson in Hadar, Ethiopia, which is a similar-ish area towards Tanzania, roughly the same quadrant of Africa. Lucy is a 20% complete skeleton, so we're going back to this idea that, again, this is not full people, it's complete. It's only 20%. Yet we have her skull, and that's the big thing. We have most of her skull that's intact, and that's the major uh, benefit that we get from Lucy herself. She is a 3 foot 7 inch tall adult female hominid Australopithecine. And we just want to be able to do that before we move on to the next slide and show you some pictures of her. It's just represent not that big. Okay, so we talk about, say, you got Victor Wembanyama, who's 7 foot whatever in the NBA, and you got all these big guys, and you got Mr. Cranmer walking around 5'10", and 3 foot 7 inches tall is not that big. You got German shepherds who are walking on their hind legs at 3 feet tall. So just understand that these are not big animals, and yet these will become and these will eventually become us today. Well, this is Lucy. This is Australopithecus afarensis, 3.85 million to 2.95 million years ago. Males are about 4 foot 11 inches tall, so about 5 feet tall. Females 3 foot 5. We just want to, again, the smallness of these animals. 3 feet 5, 64 pounds. I've had Brittany Spaniels that are almost this size, standing on their back legs. There's German Shepherds that are almost 92 pounds. So we're talking about small animals that will, again, working their way towards becoming human. Physically, this is Lucy's skull herself, and so again, fossilized within the rock. But the big thing is to be able to go and get most of her skull intact, to be able to then 3D scan the inside of it to give us a little bit of more insight on her brain. Your brain, as it pushes against the inside of your skull, it's not going to be like pushing up against it hard, but it's going to leave small indentations and no, grooves is probably not the best word, but indentations and divots on the inside of your cranium that then we can go and scan the interior of the skull and see what bumps this skull has versus doesn't. So that's why the skull is very important because the brain is going to be lost over millions of years, but the skull surviving gives us a little bit of at least insight into some of the impressions of what the brain had been. And so again, the Australopithecines are the first to walk upright for the most part, and are leaving behind some of the other evidence in the archaeological records, such as the Laetoli footprints. And again, you can kind of see very clearly on the right-hand side, we're blowing out the laser pointer, the larger individual, and on the left-hand side, the smaller individual. You can compare the two sides of the footprints to let us know and see how they are walking through this volcanic ash nearly several million years ago. So this is the type of information we're working through with our Australopithecines, and you can kind of go in and see the differences there. The next closest human ancestor to us is Homo habilis. Homo habilis dates from 2.5 million years ago, and that name translates from the Latin to English as man of skill. Homo habilis was first discovered in 1960 by Lewis and Mary Leakey, again, the Leakey archaeological team. They're working in Oldavi Gorge, Tanzania, which again is going to help explain why 14 years later they're going to be discovering in Laetoli, Tanzania, the Laetoli footprints. Homo habilis marks a big step towards modern humans, and that is a 50% larger brain than Lucy. So does it make him 50% larger? Not necessarily. Think about the blue whale having a brain the size of a Volkswagen Beetle. Right? We don't have blue whales landing on the moon. We don't have blue whales making GPS or AI. But we see that again, they're bigger brain and they're smarter than the Australopithecines and Lucy that's come before. Now they're named man of skill because what we see Homo habilis doing is using tools out of lava rock to be able to take lava rock. Again, this is an igneous rock that can be shaped and has can be shaped and worked to having a sharp edge to then be able to use that rock to cut meat and crack bones. And what we see from these lava rocks is it's not just I pick up one rock, hit it against the harder rock, and it flakes off, and now I got there. There's a couple of different steps that need to happen. You need to be able to identify a specific type or shape of this rock to then be able to go and do that to make it there. And again, the ability to cut meat and be able to crack bones becomes a big deal in order to be able to get to more protein-rich foods. Meat's going to have more protein than, not necessarily, but for most other plants, as well as to be able to crack open bones. And you want to crack open bones to be able to get into the bone marrow that's inside. Bone marrow is very calorically dense. This is why, again, the cartoon dogs are carrying around their cartoon bones. A dog chews a bone to be able to get into the marrow on the inside. So if you can break into that, you've got the marrow inside, very calorically dense, high in fats, high in proteins. You can make a pretty solid meal out of it. It's got all the things a growing body needs. And that's the big thing of why they need these tools in order to be able to get to those without having to spend the extra energy. You want to understand that your body is like a car. Energy goes in, energy is then used. So the more energy you put in, the more energy you can expend if need be. And if you are expending more energy to be able to get less calories, then that's a negative equation. So you want to be able to do less effort or a more efficient effort to be able to get to more calories. And that's how these animals are operating, particularly the animals working towards humans. Our next closest human ancestor is Homo erectus. He dates from about 1.6 million years ago, and again, translating from the Latin to upright man. Now, Homo erectus is going to be using their increased intelligence to create more and more technology. And the emphasis on Homo erectus is that they are extremely human-like in form and behavior. For all intents and purposes, modern humans are walking around in a Homo erectus skeleton. If we were to travel back in time, we hop in our time machines, hit 88 miles per hour, miles per hour and go and pick up a Homo erectus baby, bring it to New York City, raise it up, give it a shower, give it a shave, put it on the streets of New York. You might get a couple people looking over their shoulder, but most people won't bat their eye in particularly physically how they're presenting. You start talking to them and things might go out the window real fast. But Homo erectus are very skillful hunters. They're using a lot more sophisticated tools, but importantly, Homo erectus is going to be doing a couple of firsts in terms of hominid and human history. Homo erectus are going to be the first to use fire. And what we mean by using fire is not that, oh, a wildfire started, I'm going to exploit it, to be able to create fire, manage fire, and use it as a resource. Now, they're going to do it for a lot of different things. Obviously, fire provides warmth. And again, we're trying to conserve calories. If I'm spending all day to be able to get a cup of berries, right? That's not a lot of calories. I don't want to spend all night shivering, using up those precious calories. I want to be able to use that going into my brain to be able to go with calculus and uh, submarines and airplanes. I don't want to be using wasting those calories shivering. So it provides warmth, provides smoke, right? Smoke keeps away bugs and other animals, right? Again, fire will go and keep away lions and tigers and bear, oh my, on the savannas, right? To kind of protect yourself in there. Fire provides light in the middle of the night. It extends your working hours, extends your ability to see, provides a little bit more protection, a little bit more safety. The big thing fire provides, and this is why it's capitalized, is the cooking of food, particularly of meat. When you go and you cook meat, we see a chemical change at the chemical level of the meat, making it easier to digest. Raw meat can be consumed and can be used by humans, but if we take that meat and we cook it, we're doing a couple different things. Number one, you're cooking out a lot of different parasites or other bugs and some bacteria from there, so you get that plus, so it's a little bit safer in the sense of food safety wise to be able to eat. Secondly, and more importantly, is that on a chemical level, right, the sugars, there's a reaction making it that becomes easier for human beings, right, and hominids to be able to digest it. Meaning that think about what happens after Thanksgiving, after everybody's having a big, huge, giant meal. For some people, the largest meals they're going to eat all year. Everybody collapses on the couch because they're in a food coma, because their body is spending a lot of energy digesting that giant meal that they had. So if you cook food, it makes it easier to digest. You are spending less calories to digest it. You can spend more calories in your brain, walking to get even more calories, and that becomes the big change there, and that's the important thing. Pandas are dumb, stupid animals. Pandas have evolved to really only eat bamboo. Pandas have a really tough time digesting bamboo. So they are going to spend, it's like 22 hours a day eating bamboo, or 22 hours a day sleeping, so they can spend 1.5 hours a day going and then eating the bamboo. And it becomes kind of like, well, there's not a lot left time left over to make baby pandas. And so that's the building about what cooking food allows you to digest it easier. Homo erectus is one of the first hominids that we know moved out of Africa. So we're going to see pulses of exodus of hominids out of Africa through our history working towards modern humans. But we know that they're one of the first to move out of Africa because we have Homo erectus skeletons in India, in China, and in Europe. Now, they may have been the first to be able to use a spoken language. And again, may is capitalized and italicized there for a reason. On our brains, what's allowing me to speak to you and what's allowing you to understand what I'm saying is a bump on your brain called Broca's area. It's basically what we figured out to be able to language comes from in modern humans. Remember when we talked about skulls, your brain is going to push up against the interior of the skull with some of those bumps. This bump is on the outside, and we know that looking at Homo erectus skulls, they have where their brain would have been this bump. Now, that doesn't necessarily mean just because they have that bump that they are going to be able to have a spoken language, but they could have been, and with Homo erectus, we see this being used, not being used, but see this anatomically for the first time. And so that's the big idea. I mean, I've got the same build as Usain, I'm not the same build, but the same body as Usain Bolt, and yet I can't run a 9.75 and 9.7. I can't run an under 10 100-meter dash, right? Just because we have the same parts doesn't necessarily mean we can do the same things, but it's the idea there that in theory, I've got all the physical things on my body to run that fast. I'm that doesn't necessarily mean I can do that. So we're working our way through that. We can kind of see as we're working our way from the Australopithecines on the right there, working our way towards the Homo erectuses with the Homo habilis in the between there. So Homo habilis about 2.4 to 1.4 million years ago, 3 feet 4 inches tall to 4 feet 5 inches tall, so we're a little bit bigger, averaging about 70 pounds between males and females. Homo erectus, we can start to see looking a little bit more human, like 1.89 million to 143,000 years ago. 4'9", 6 foot 1 inches, 88 to 150 pounds. We're starting to see modern human sizes. All right, we can find people in Joliet Catholic, all right, find people on the street that are starting to fit those heights and weights to be able to make them more human in appearance, and again, a little bit more in how they're interacting with their environment as we start to go and see them. So Homo habilis, again, the early one, Johnny's Child is the famous one. They're making the first stone tools. And then Homo erectus, again, the first to move out of Africa, we think the first to be able to control fire, and then be able to go and the first to be able to move into different places. And again, the big thing here is that we see several different Homo erectuses throughout most of Eurasia and from Africa, and it's that pulse out of there that we begin to go and see some other stuff. Now, we're going to touch on really quickly another human ancestor, the Denisovans. And this is cutting edge stuff. It's not even in your textbook from the early 2000s, but this is something we've, in the last 10, 15 years, we found an individual of that, and we're starting to do that. And what we understand is that modern day humans have some Denisovanan DNA as well. So they are, we're going to think of a far distant removed cousin, but when we're learning more and more about them, and we can go and put in there, and it would not be, um, I would not be surprised that in our next textbook that we get here at the school, or that what your grandkids will be taught, will be adding Denisovans to the human tree as well. And again, that's the cutting edge nature of this to be able to go in and put these humans and human-like stuff there. So we're going to pause there in our story. We're going to leave with the Denisovans as the most human-like hominids that we've come across so far. The Homo erectuses are right on the way. And then again, we're going to begin to move into even more human-like hominids, as well as talk about modern humans in our next lecture.